Hi guys, it's your guy Olumide, and today we'll be solving another one of the most commonly asked tech interview question. It's the matrix infection. The matrix infection is a DSA problem that's commonly asked by top tech companies including Google, Amazon, Meta, Microsoft, Apple, and other top tech companies. The problem statement states that you are given a matrix where each cell is either empty, uninfected, or infected. Empty is represented as 0, uninfected is represented as a 1, while infected is represented as a 2. With each passing second, every infected cell represented as a 2 infects its uninfected neighboring cell that is represented as a 1 that are 4 directionally adjacent. Determine the number of seconds required for all uninfected cells to be infected. If this is impossible, we want to return -1. So, and we are giving this example inputs. So we say that at the very 0 seconds means that at the start time, we say that only 2. We have only 1 infected cell, right? Now, according to the problem description, the infected cell is going to infect its uninfected neighboring cell with every passing seconds. So at this particular second 0, now this infected cell is going to infect its neighbors, uninfected neighbors, right? So this is neighbor 1, 2, 3. This neighbor up here, up, left, right, and down. This is its neighbor. Now uninfected neighbor, this an uninfected neighbor, so it's going to be infected and it's going to become 2, and that's how it become here. And similarly, at the same seconds, this is neighbor also going to be infected and becomes 2 here, right? So, and similarly down here, this one also becomes 2. But you see that 0 is empty, so because of it's actually not, it's just an empty cell, so it's remain like that. Now, these are all the cells that are infected at the second 0. Now, after that, at the seconds 1, these newly infected cells are going to infect their uninfected neighboring cell, right? Like this 2 now that is nearly infected is also gonna infect its neighbor 1 right here, and that becomes 2. And similarly, this newly infected cell also is gonna infect a neighbor 1 right here, and that becomes 2. And you see that now these are all the newly infected cell could do. So now in the third seconds, now this again newly infected cell here is gonna infect its nearest neighbor and becomes 2. And then this newly infected one actually does not have any neighbor to infect because its neighbors are empty while the rest are already infected, right? So now it means that it takes 3 seconds for all its neighbors to get infected. So the first one infect the first 3, then the second one infect the newly 3 infect actually 1 right here, while this particular one right here then infect this last one, and it takes actually 3 seconds to get all the uninfected neighboring cells infected. To solve this problem, let's consider a simple version of the problem whereby there's just one infected cell in the matrix. So let's consider this example here whereby there's just one infected cell in the matrix. We see that the matrix can be represented as a graph data structure whereby the infected and the uninfected cell are represented as nodes, and then the neighboring cell, the 4 directional neighboring cell, can be represented as edges or connection between these infected and non-infected cells. So just like you can have here, so whereby we have the node 2 corresponding to cell 2, and then node 1 corresponding to cell 1. This suggests that we need a graph traversal algorithm in order to be able to infect neighboring cells. And to decide which particular type of traversal algorithm we're going to be using, let's consider the problem again. Okay, we're going to be considering how the infected cells are going to be infecting neighboring cells. We see that at the first time it's just only, we see that at the first time it's just only these two. It's just only this cell, this particular cell here, that is infected, right? So now in the next one, in the next seconds, right, when seconds equals to 1, every neighboring cells, you understand, to this particular cell is infected now. That is, every cell that are at a distance 1 to that particular cell, these 3 cells are distance 1 to this particular cells, are now infected. And then at the seconds 2, we see that those that are at a distance 2 are now infected, meaning that this particular one here and this one here are infected. So one thing we can draw out of this is that at each seconds, we make sure that every infected cell have the opportunity to infect their neighboring cell, and once every possible infected cell at that particular seconds infect the neighboring cell, this neighboring cell will be the new infected cell. There will be the newly infected cell. What I'm trying to say in essence is that at second 0, right, only 2, we have only 1 infected cell in the whole matrix, and this infected cell is gonna infect its neighboring cell. Now this neighboring cell now form another network of infected cell, right, because they are now infected. So they are the one that form the second one, meaning that at the second one, these are the newly infected cell. Now this newly infected cell will now form the next newly infected cell by what? By this particular one infecting this and this particular one infecting this, in such a way that at seconds 2 we now have 2 newly infected cell, meaning that this 2 newly infected cell is what constitutes the newly infected cell. So now again, this set of infected cell now will infect their neighboring cell to form the third sequence, right? And then at this point we see that this is just the only one infected, right? And then at this point we see that there is no more infected cell. So looking at this, we see that it follows a particular type of breadth first search method, which is actually a graph traversal algorithm. You understand? If you have been following my previous videos on graph, you understand the breadth first search method, and this particular problem follow the level order, meaning that it is actually like they are infecting or level by level. At first it's just one infected cell, and now this infected cell actually infects its neighboring cell to bring up another level of infected cell. This new level now will infect their neighboring cell. All of them together will infect the neighboring cell to bring up the second level, which is the second sequence, right? So, and then this one will bring, and then the next newly infected cell, all of them will collate and join out together to bring up the new level and new set of infected cell, which is the third level, meaning that we'll be using the breadth first transversal, which is the also we are going to be using the particularly the level order transversal, whereby at each second equals to 0, 1, 2, we denote a level. Is like level 0, level 1, level 2. So at level 0, for a situation whereby the matrix only contain one infected cell, at level 0 we have only one infected cell, right? At level 1 it will be composed of the neighboring infected cell to that particular one, so that will constitute the next level. And then level 2 will now, which corresponds to the second 2, right? We have the second 0 or level 0 that actually corresponds to the infected cell, the only infected cell, right? Because we are dealing with matrix with one infected cell. So now level 1 is gonna correspond to its neighboring infected cell, right? So level 2 is gonna correspond to the neighbors of this neighboring infected cell. So, and that way we can effectively solve this problem. But now let's consider a situation whereby matrix contains multiple infected cell, right? Look in this particular matrix infection board, so whereby we have 3 infected cells. So this is the graphical representation, whereby the infected and non-infected cell actually represent the nodes, and then the edges are represented by their horizontal and vertical neighbors, right? So in this now we have 3 infected cell at the very 0 seconds, right? At the very level 0 they are already 3. So how do we solve this problem? To solve this problem, because if we pick only one of them now, and we treat them like a matrix with only one infected cell, it's gonna cause a problem. Why? Because these three infected cell actually corresponds to the same level, right? What I'm trying to say is that these three infected cell, they are actually in level 0. Why? Because at the very seconds equals to 0, at that very seconds we have 2 infected cell by default and 3 infected cell by default. So what we are gonna do is that in our queue, don't forget I talked about using BFS, the breadth first search, which actually utilizes a queue. You can go back to my previous video on trees, on graphs. I've actually done I've solved a series of problems using the breadth first search method. So it uses a queue, right? So, and then what this implies is that instead of just adding one of the infected cells into the queue, initially the queue will be made up of all possible infected cells at level 0, so that all of these possible infected cells is gonna give birth to the next possible infected cell, which is gonna be the new level 1, right? So meaning that we are gonna, so in our queue we're gonna be putting in a tuple, right? So it's gonna be the coordinate of each of the infected cells. So this is 0,1 for this, and this is 2,1, I mean row 2 column 1, right? And for this is 2,4, row 2 column 4, right? Okay, and then what we do is that we are going to populate our queue with these particular details of all infected cell for the very first level, so that they will constitute our second equals to 0. So now to move to second equals to 1, each of them are going to affect their neighboring cell. So you see that this one is going to affect this here and this here. We talked about using the BFS transversal, right? So whereby we're gonna try to tap into all their old direction, we're gonna tap into all their own neighbor, so that at that particular level. Let's go into the code implementation for our matrix infection problem. So we're gonna be taking in an argument matrix, which is a list of integers, and the return is going to be an integer, so which will represent the seconds. So let's collect the length of the matrix, which represent the rows in the matrix, as well as the column of the matrix, so that represent the rows and the columns. Okay, so also we will be defining our ones. Don't forget our ones is gonna keep track of how many ones we encounter. So we also wanna define the second and set it to -1. So we're gonna be setting to -1, and you will get to know at because you know it is 0 index, so the very first iteration will be 0, the second will be 1. So if as you can see in the problem statement, you see that it starts from 0, not 1. So we have to set our and initialize our seconds to be -1. So now let's also define our DIRS, which is going to represent the horizontal and vertical neighboring cells. So we're gonna set it to 1,0, 0,1, right? 0,1, 0, -1, and it can be in any order, since we are just gonna iterate through it. -1,0, but what is important is the what is inside row and column. So right, okay, now let's iterate through the cell. Let's iterate through each cell in the matrix, for row in the range of row, and for each column as well in the range of columns m n. So what we want to do is that we want to check for all the infected cells, and also want to keep track of the ones. So you don't forget that all the infected cells that is initially in the matrix is what will constitute 0, right? Is what is going to constitute second equals to 0, that is the very first level of infected cell. So and that leads us to an important observation. We have to import our from collections. We want to import the queue, right? So because we'll be using the BFS method, the breadth first slash method, so which uses a queue. So you'll get to know what I'm trying to talk about now. The queue. So right now, that way we can easily add each of the infected cell, their coordinates. We can add them into the queue. So iterating through it now, if matrix of R of C if is equals to a 1, right, then we want to increase our ones by 1, so that it will detect that we found one more cell with one more uninfected cell, so that once we start to infect these cells, we can keep track of how many cells are remaining and how many are yet to be infected. So but in a situation whereby if matrix, or let's say a leaf, because there's no way a value wants to be 2, it's only gonna be either 1 or 2 or 0. A leaf matrix is equals to, matrix of R of C is equals to a 2. If it's equals to a 2, what we want to do is that we want to add to our queue. So q dot append the coordinates, so it will be a tuple of R comma C, so that we can keep track of the coordinates that actually is an infected cell. So and that's what we want to do at first. So after doing that, now while q, we want to keep this on until we get every cell infected, right? So while q, because we know quite well that q is composed of infected cells, so once there's still infected cells within our queue, we just want to keep repeating this block of code. And what we want to repeat is, first of all, we want to increase our second by 1. So you see why I set it to 0 at first is so to -1 at first is so that at the very first iteration, whereby our queue composed of the original and initially infected cell, don't forget that's what it composed of at first, so it's gonna set the second to 0 at that point. So that's how we solve problem logically. So we don't just set this value like that, but based on logical terms, that okay, at the point whereby the queue actually consists of initially infected cell, maybe 1, maybe 2, but just as it is given to us in the problem statement, we want our seconds to be 0, so we have to preset our seconds to be -1 at first. So now what we want to do is that first we want to collect the length of our infected cells in the queue, right? So that will be length of the queue. So and why we are collecting it is because we are gonna be those particular length of infected cells is what constitutes this particular level, this particular second. So we just want to iterate up to that length, so that by the time we iterate up to that length, we can be sure that we have iterated through that particular infected cell that particular level. So we know that any other infected cell inside will correspond to the next level, and so that that way we can increment our second by 1, because there are still infected cell in the next level. So for underscoring range of length of infected cells, what we want to do is I want to pop out each infected cell in that level. So and we do it by doing q dot pop left, right? So now we're gonna pop left. Now we have the particular infected cell, and don't forget that this infected cell is actually represented by a tuple that represents the row and column of that particular corresponding cell that is infected. So what we now do is that we want to iterate through its horizontal and vertical cells, right? So to try to check for any uninfected cell. So we're gonna see for dir in dirs, so we can check for any uninfected cell so we can get them infected. So rho equals to r plus dir of 0, and similarly when I get to the column as well, column equals to c plus dir of 1. So because we know dir of 0 corresponds to the uninfected and corresponds to the row, while dir of 1 corresponds to the column. So this is what I mean by dir. So they are actually coordinates, like I explained earlier. So right now that we have our row and column, so what we now do is that we want to try to check if it's within bound. If it's within bounds, so if it's within bounds of row and column and matrix. So what we mean by this is that we're going to be defining a function, right? We're going to call the function is within bounds. So it's going to try to check if that row, don't forget that row and column actually corresponds to indices in the matrix. So if this index is not going to give us an index error if it's within the range of the matrix. So that's what we just want to check before we proceed to index it. So it's just like we are trying to cache the exemption in case if there's an error, if there's an exception. So then we just want to proceed to get row and column. So if it is valid, then we go and index that corresponding cell, and we try to check if it is equals to a 1. So don't forget that now we have gotten the we've gotten the particularly infected cell by popping out of the queue. Now I want to go and get its adjacent cells, so the ones that are not infected, that is the one that are 1. We want to get them, and what we want to do is that we want to set them to a 2, right? So meaning that we want to get them infected by setting it to 2. So it's equals to 2. After setting their value to 2, we also want to add them into the queue, because they are now infected and they are going to constitute the next level of infected cell, that is the level 1, level 2, level 3, something like that. So q dot append, want to append the, and what are we appending is the tuple of the row and column. So it represents the coordinate of that infected cell. So and then we reduce our ones by 1. And why we are doing this is because this particular cell is an uninfected cell now, and we have made it infected. We have to keep track of the remaining uninfected cells in the matrix. So right, after doing this, this is quite all we want to do. So we just keep doing this on and on until there is no more infected cell in the queue any longer. So at that point we can just loop out. And then what we're gonna do whenever there's no more uninfected cell in the queue is that we just want to return the second, right? So don't forget we define the variable second. So we return second if there's no more infected cell. So if not once, that is if there is no more uninfected cell in the matrix, then return 1, else return -1. So in the situation whereby there are still uninfected cells that could not be reached by the infected cell, that is there are still some ones among the matrices, then definitely we are going to return -1. But in the situation whereby all ones have been converted to infected, have been made to, then when I return the seconds, that is the time that it takes to, the number of loop that it takes to actually infect every one of the cells. So now we have this matrix, and then we have our print statement. So let's try to run this code and see. Well, the code is gonna give us an error except we define the is within bound function that we talked about. So to help us keep track of whether the bound is really valid or not. So integer, so and then a matrix. So this is what we are sending in, the argument we are sending it into the is within bound.